Okay, let's take a look at two more situations. In the previous video, we looked at an object that was fairly close to the focal point, but not quite there. It's between the focal length and twice that distance. It's kind of in here somewhere. And we noticed that we would get a real inverted image over here, but it would be further away from the lens. Okay, but it was bigger, upside down. It was real. We could see it with a screen. It's over in this range. Now let's take our object. Let's say it's a filament. And let's back it way up. In this case, we're well beyond like 3 times the focal length. So we're like 30 centimeters or more away. So we're way out there. All right, let's see how that affects where things end up. So we're going to start the same way. We're going to take a ray that comes out parallel. It's going to hit that lens, and it's going to go through the focal point on the other side. Then we're going to take a ray that comes out and goes through this focal point, hits the lens, and comes out parallel. Now this isn't a perfect drawing, but what I can see is all of a sudden those rays are crossing and converging inside that second, twice the focal length, that distance. But previously our image was over here. Now this is still a real image. You guys saw this with your screens. You could put it there and you could always see this image show up. It's real, it's inverted, but this is slightly different. This one is smaller. Look at the length of this arrow versus the length of this arrow. It's a little bit smaller. Not by a ton, but a little bit. We won't do all the math on it right now, but you should get it to end up at least measurably smaller. Now, you guys saw this happen a lot. We would move that bulb around, and if you got the bulb real close in here, all of a sudden you would see a gigantic image, and it would get way far away. Sometimes you'd project it on the wall. If you move that bulb back a ways, all of a sudden you would get a really small inverted image. It was easy to work with because it didn't move very far away. You could always find it with that screen, but it was small nonetheless, so sometimes it was hard to see features of it. So it just depends on where you're at. This is kind of the key spot. If I'm outside of this, I get a tinier image, and it's closer to the lens. If I move this inside that 2F spot, all of a sudden my image now gets bigger, and it's beyond the lens. It's further away. Okay. Now, those two are fairly easy to see. This one's tough, but you guys have actually done this many times outside of physics class. You just don't realize you're doing it. So here I took the object and I'm moving it really close. Like if this is 10 centimeters, this is like 5. It's really close. It's inside that focal length. Okay, now when that happens, and you go to draw this is where it gets a little tricky. You have to use your imagination. I'm going to draw a ray coming out parallel. Okay, but then when it does its bend and it goes through that lens, it's going to come through the focal point on the other side. That one's not so bad. However, it's hard to draw a ray going through this focal point because it's not the direction I'm looking for. However, we did this with mirrors, and it's just going to take a little bit of creativity on your part. Let's pretend we have a ray coming through this focal point. So it's coming from that direction. It's going to hit the lens, and then it's going to come out parallel. Now the big difference here is nothing happens on this side. Like there's nowhere where those sets of rays converge. They just go away from each other. So if I get this really close to the lens, these rays on this side just spread out. They don't converge, so I get no real image. But it doesn't mean I don't get an image at all. Okay? So this is the kind where if I put a screen right here, I see nothing. I move it around, I still see nothing. I just see light. I don't see any specific shape. However, if I get rid of that screen and I put my eye somewhere over here, so let's say I put my eyeball right here and I'm looking back through the lens, well, my eye is catching this set of rays right here, and my eye doesn't really know that this set of rays came from over here. It has no idea that it bent. It just projects the direction that it looks like it came from. So my eye thinks those rays came from back here. Okay, if I move my eye around and let's say I put my eye right here. Okay, it's going to be catching this set of rays that crosses right at my pupil, and it interprets that direction as, hey, those rays must have come from way back here. It doesn't know that it got bent by the lens. It just projects where it looks like it came from. And no matter where I move my eye, remember, we're only drawing 2 sets of rays, but there's really thousands of these things. So wherever I'm at, I'm catching a set of rays that is bending by the lens, but I can't really tell. And my eye and my brain just projects backwards where it looks like it came from. And it looks like it came from right here. This is a virtual image, and this is what a magnifying glass does. I look through the magnifying glass and I put the object on the other side. So light's coming off this object, but what I'm really getting is a virtual image that looks bigger and it's upright. You notice in magnifying glasses, you don't ever have an upside down image to worry about. It's always right side up. It's upright and it's bigger. And as long as that object is within the focal length here, within that 10 centimeters for this lens, I'm going to see a much bigger version. And it might look like it moves way back and it gets gigantic. It might look like it's not that much bigger. It all depends on how I play around with this distance right here. Okay, but nevertheless, I get a bigger image. I have to look back through the lens to see it. And if I put a screen here, I don't see anything. So it's not a real image. It shows up on a screen, but it's definitely something that's there. Okay, so that's how you get a virtual image with a convex lens.